The next topic will be the concept of convolution. Right. So convolution is basically a mathematical process. Uh, in terms of the signals, right? Let us say we have two different signals and you can perform the operation called as convolution between the two signals. That is represented by, right, the following notation. Okay. So let me say I want to calculate a output y of n, which is equal to the convolution of two signals. Let me say this is x of n. This is the notation for convolution. It is a star, okay, h of n, right? So mathematically what you are going to perform, right, is like this. Here, this is the sum, therefore summation k is equal to minus infinity to plus infinity x of k into the h of n minus k. So this is the equation. I'll tell you what exactly the meaning of these equations. Okay, so this is what is the representation, right? I can actually rewrite the same thing in a different way. So the y of n can actually be calculated in the same fashion like convolving the h of n with the x of n. The result still remains same, though the equation wise representation changes now. Okay, so if I try to write the similar equation for this, then this is k equal to minus infinity to plus infinity. You have h of k circular, sorry, it's a convolution, x of n minus k. But remember, both are equal, both are same, right? Both will give you the same answer, right? The result of convolution is same, irrespective of the way you convolve. Okay, that's the first point. So normally this is actually the discrete calculation. So this convolution equation, whatever I have written so far, is the discrete, right? So this is for discrete signals. Whereas we have another version that is called as the continuous version of the convolution. Okay, so we have a name for this. So I'll write the name. Discrete signals. This equation is called as the convolution. This is convolution sum, because I can see that there is a summation. Summation indicates you are taking the sum of something. That's why it is called as a convolution sum. Same thing holds good for this equation as well. Okay, that's also a convolution sum. Now, let us say we have slightly different versions of signals. They are called as the continuous signals. Okay. For continuous signals or functions, right? The convolution, say y of t. T is a continuous variable. Okay, so for continuous signals, the convolution result y of t is equal to, this is x of t convolution h of t. Now there is a difference in terms of the way you calculate. So now since it is continuous, I cannot take a sum. This has to be the integral. So integral tau is equal to minus infinity to plus infinity, right? So x of tau into h of t minus tau. Variable of integration is d tau. So just compare it with the previous equation so that you get a clear idea what exactly is happening. So it's right now what we are writing is equivalent of this term. So there is no summation, there is a integration. Okay, so replace the summation with the integral. So what is the variable, right? I don't use k now, I use tau, minus infinity to infinity. And x, there is x of k, right? I write x of tau instead of this. Then h of n minus k becomes h of t minus tau, because t is my continuous variable, tau is the variable of integration, right? So we apply that. So, and as a result, right, you can see that we will be able to get the final answer in this particular fashion. Just give me one second. All right, I just have to answer one call. Sorry. Okay, so these are the two different types of equations, right? One for continuous signals, one for discrete. Okay, out of which we are not going to consider the continuous case now because we are not dealing with any of the continuous variables here. But since I wanted you to make sure that you should know that there are two types, right? I just wrote that equation, but we will not look at the continuous case as of now. Okay, because the maybe the image or any signal that we are going to consider practically will be a discrete variable. All right. Okay. So we are going to look at the convolution of the discrete. Okay. But I just have to write one name here. So this particular calculation is called as the convolution integral. Okay. It is not sum, it is integral. Convolution integral. All right. Moving ahead. Now, let's look at the discrete case, and there are many ways in which you can perform the convolution of the discrete functions. Okay, so let's look at the first and the easiest representation, right? That is called as convolution using the delta, right? The delta notations. So delta is actually, right? It is the delta of n is nothing but this is called as a unit impulse, right? It's a unit impulse signal or a function that is denoted by this signal is 1 at n equal to 0 and this is 0, right? Else. At any other point, right, it is not uh, it's not there, it's 0. For example, if I want to plot and show you how this looks like, so this is the plot. So this is the horizontal axis. Let me call this is the n axis. I'm plotting n. This is n equal to 0. At n equal to 0, this signal has amplitude equal to 1. And it's not going to have at any other point, it has no amplitude. Right? So this signal has an amplitude. I'll mark a amplitude, the head of this function, and I write 1 over there. It is at 0. At any point 1, 2, you see its value is 0. It's not there. At minus 1, at minus 2, it is not there. Okay, this kind of function is called as a unit impulse function. It is unit because its amplitude is 1. Okay, right. So we try to represent any given function using the delta notation first, and then we use the property of a delta function to perform the convolution. This is the first and the easiest way. Okay, all right. Now let's try to look at the properties of delta functions only with respect to the convolution. I'm not going to write any other property, right? So this is how it works. Okay, so I'm going to first tell you about the convolution property of the delta, right? So whenever I perform the convolution, let us say I face a convolution of delta of n minus m into the delta of n minus k. So this can be replaced by simply delta of n minus m minus k. So this is the straightforward result. We are going to use this itself to plot, okay, to get a result of the convolution, right? Only one property, right? There are many properties of delta function, but as of now, since our intention is just to look at the whole concept of convolution, we are not going to look at anything other than this. Okay, only one property will remain. Okay, now in which so far I know that only what is delta of n, but I don't know what is n minus m, right? Or maybe in some other cases you may face n plus m as well. Okay, what is that? We'll see quickly. Right. So before applying this particular function, we'll look at the right. All right, let's see. Right. So if I have delta of n minus, right, let me write this. So I have, say, delta of n with me. If at all I convert this into delta of n minus whatever, maybe m, right? So this particular property, this sorry, this is not a property, this is an operation, right, on n axis. This operation is called as a shifting operation. All right. Now, what type of shifts you have? Let me see. Okay, so let me say this, there is a function delta of n, and I have two types of operations possible. The first operation, if say this m is positive, this is because n is a number, m is also number. Both m and n are integers. If m is a positive integer, then the shift is actually called as the right shift. Okay, I'm shifting the signal function to right. At the same time, if the m is, say, negative, right, then that is a left shift. Let me show you, right? Quickly, let's go through that. Right, so let me write the delta of n. I know that the delta n is, right, a simple function. It has x-axis. This is the horizontal axis. I'm going to call this is n, and see the amplitude is like this. All right, so this is 1 at 0. Now let me say I want to perform, right, the simplest one, which is the right shift, right? I'll simply plot delta of n minus 2, right? M is positive, you can see here delta of n minus m, and m is positive. How much? M is equal to 2, right? So here the right shift by, I just write, this is how much shift I should write. So the when m is positive, right shift the delta of n, right? I'll write right shift the delta of n by m units, right? So left shift the delta of n by, once again, m units. Okay, so now you see, let me say m equal to plus 2. When m equal to plus 2, I simply replace m by 2. So this becomes delta of n minus 2. What is the idea? The idea is that you have to shift it right by 2 units. In the sense, whatever is at 0 will go to 2. Okay, so let's quickly plot that. So this means this is what my signal looks like, right? So the same delta function, instead of, see, this is at 0, now it shifts to right by 2 units. At 2 you have the same function. Okay, amplitude is 1, and right, so you see this is 1, right? It is shifted to right by 2 units. Magnitude remains same, right? So what I did just now is, right, this is nothing but the delta of n minus 2. So the shift is by 2 units. Now let me say m equal to minus 3. So what happens to your delta function? This is delta of n. By default, it is minus, right? Delta of n minus, the m is minus 3. So minus of minus becomes plus. So you have n plus 3 is the representation. Okay, now as per this, shift the function to left by so many units. M is equal to minus 3 means the 3 units I should shift the function to left. All right, so let me show you this. So this is the n. I am assuming that this is 0. So this is minus 1. This is minus 2. and say this is -3. So the same function, instead of at 0, you have to write the function where the function is written at m equal to 3. M equal to -3, my mistake. Okay, so at m equal to -3, you write this amplitude is still 1, but see the position is changed. Okay, so this kind of operation, right, is what is the shifting operation. So when I come on this part, I'm trying to plot the delta of n plus 3. Okay, all right. So that's how the fundamental things are going to work for us now. Okay, let us see. Now you can see here, right? So now I'll come back to the convolution property of this, right? So what does the convolution property says, right? If you have two shifted versions of your delta functions, you can convolve like this using this particular property. Okay, so that's all. That's the only simplest property which we can use so that we can convolve. Okay, now let's move ahead. Let's directly go to a problem, right? So before going to the actual problem of the convolution, right, I need to know that how do I represent any given function in terms of delta? Okay, so the next topic that we are going to discuss is, right, a representation of functions or the signals using delta of n. So how do I do this? How can I represent any given function, right? Or any given signal in the form of a delta? Okay. So let's go for an example, right? So the example is like this. So let me say the given function x of n is equal to, let's try to represent this. Say it is 1, 2, say 4, -2, 3. Okay, let's try to keep this 3 and say 1. Okay, normally this kind of representation requires an indexing, in the sense this signal might be present anywhere on your time axis, correct? For example, if I say this is my n axis, maybe it actually starts from 0 itself, 0, 1, 2, 3, 4. Like if this is 0, 1, 2, 3, 4, 5, 0 till 5, maybe the amplitude is 1, 2, this is 4, this is -2, and say this is 3, and this is 1. Possible. Okay, but you see the same signal may be starting at 5. So if it is 5, right, it is this the next point will be 6, 7, 8, 9, 10, right? You see that there is an importance of indexing as well. Where the signal starts, I need to mention. So just to identify where the signal starts, the easiest way in terms of the representation is you just put an arrow mark wherever there is a 0. For example, right, if I assume right now, I am going to assume that my function is starting at 0. So what I do, I'll simply put an arrow mark over here saying that that is a 0th index. Okay, so wherever you put, that means it is a 0th index. So just to make things easier for you, let me try to plot. Okay, let me try to plot this for you. Okay, so this would be the x of x. This should be n. So I understand that signal starts at 0 and goes all the way till 5, because if the arrow mark is 0, so next one will be 1, 2, 3, 4, 5. So indexing is along n axis and the amplitude will come along this. So if I say this is 1, say this is 2, maybe, okay, I'll make sure that I can plot more. So I'll reduce the scale. So this is 1, say this is 2, this is 3, and say this is amplitude 4. Similarly, I have negative 2 to be plotted. So this is -1. Say this is -2. Okay, so now look at the plotting. So this is at 0, it is 1. Okay, I'll change the color for the plot. So this is the at 0, its amplitude is 1. Okay, so this is the signal. Then at 1, the amplitude is how much? The amplitude is 2, right? So this is the function. Okay, and at 2, the amplitude is 4. Okay, so this is the plot. Then at 3, it is -2. Okay, so at 3, it is say -2. And at 4, it is 3. And at 5, how much? It is 1. Okay, so this is the plot. Now you see, if at all I want to write this particular function by using a delta function, what is the representation of this one? Right? This is a delta function itself, correct? So when I say that is my delta function, right? Now I'll parallelly write my equation. Okay, so the equation for x of n I'm trying to write now. So x of n equal to, I don't want to write like this. I don't want to write the numbers. I simply want to convert them into the equation format. So what is this? The first sample is, right, delta of n. So let me write delta of n. Okay, now you see, what is this sample? The sample is located at +1, means the delta function is shifted to right by 1 unit, correct? So any delta function shifted to right by 1 unit is represented by delta of n minus 1. But you see the difference? Its amplitude is not 1, amplitude is 2. So, right, I need to multiply this by 2. So 2 into delta n minus 1. Are you okay? Next number. So the next sample which is represented at 2 has a magnitude 4, and I have to multiply that with the delta of n minus 2. Delta of n minus 2 is what? Delta of n minus 2 is 6, simply this function. Okay, whatever you see in the dark color, black color. But its amplitude is being 4 here, so you multiply that 1 into 4. Because amplitude of delta function is 1, I have to multiply by 4 to reach the magnitude as 4. Okay, so that's what I did. Next one you see, it's a negative, -2. So this is minus 2 into delta of n minus 3. Okay, so you see, I'm writing the equation format. Then the fourth sample, sorry, 0, 1, 2, 3, 4. The sample at 4 is plus 3 times delta of how much? This is n minus 4. And the last one is plus 1 into delta of n minus 5. So the signal which was originally given like this, correct? Like this, right? You are converting that into the equation format, and this is how the equation looks like. I just repeat what we have done so far. Okay. So you see the original given function is this one, right? 1, 2, minus 4, minus 2, 3, and 1. Again, this arrow mark indicates where the signal starts or where is the zero index. Now I understand that zero index is at 1. So I plotted this graph, right? So the magnitude equal to the value of the samples given over here, and indexing according to the arrow. So arrow mark is the zeroth index. So I started the function from 0. Okay, so you can see 0, 2, 4, minus 2, 3, and 1. Right. This is what is my first step. Once that is done, in my next step, what I'm supposed to do, I just have to look at this graph and I have to convert that into the delta function. So delta, whatever is present at 0 is directly represented by delta function. Amplitude is 1, so it is 1 into delta of n. Okay, right. Then if at all, I'll make a change now. If assume that this value is not 1, instead of that you had a 3 here, right, at this position. So this will go till 3. In that case, right, your function would have been 3 times delta of n. Okay, only that's the difference. Okay, now it is given 1, so I have written that as a delta of n. Let's move one by one sample you need to consider. I'll move on to the next sample whose amplitude is 2 and it is located at 1. In the sense, original delta function which is located at 0 needs to be shifted to right by 1 unit. Correct? So right shift means delta of n minus k for k shift. Now shift is 1, so this is delta of n minus 1. Right, but I see that there is an amplitude change and the amplitude is not 1, it is 2. So when the amplitude is 2, I have to multiply this by 2. So 2 times delta of n minus 1 is the equation of this. So for my previous value, I add this, right? So that's why delta of n plus 2 times delta of n minus 1. Now repeat this further. Add the next sample as well. So next sample value amplitude is 4 located at 2. So any sample located at 2 is delta of n minus 2 into 4 for the magnitude, right? Next sample is minus 2. So I have a magnitude is minus 2 located at plus 3. So delta of n minus 3, right? And so on. Go to the next sample, which is at 4. So this is delta of n minus 4 into 3 and so on. Okay, so this is how you try to represent the given, any given function using the delta. This is important for us because I have to represent any function given using delta before I do the convolution. Okay. All right, let me give a function so that you can represent that using the delta function. So the sample is, this is minus 2.5, this is 3, then 4, 0, minus 1.5, this is 3.5, minus 5.5, and this is the 0th index. Please try to represent this using the delta of n function and then we'll verify. Yeah, see, you will start from the first value, right? Because that has to be represented. But you see, this is present at minus 2, right? So this is the index 0, this is index 1, index 2, 3. You start with the index where the signal starts. Okay, so this is minus 1, this is minus 2. So your previous, the previous problem was starting at 0 and that itself was a starting index. But for this problem, you can see that signal actually starts at minus 2, right? And I have to start from the starting index of that one. So why the arrow mark is given here? Just to indicate or you just to make you to decide that where this function starts. Okay. All right. So just use that and make the changes in your answer. So we can understand from this, the indexing begins at where? Indexing begins at minus 2. So, right, when m is equal to minus 2, my function is delta of n plus 2, correct? So the equation, right, h of n is equal to, amplitude is minus 2.5, but it is located at where? Minus 2. So this becomes n minus minus 2, so n plus 2. Okay, next number, this is 3 times delta of n plus 1. Next, plus 4 times. 4 is located where? At 0. So that is delta of n minus 0. So delta of n itself. Okay, so that is n. Next, plus. You see 0 into whatever, it's not required. You don't have to write that one. So 0 into delta of n minus 1. because it is located at plus 1. Don't write that, then go to the next number. So this is minus 1.5 delta of n minus 2. Right, then plus 3.5 delta of n minus 3 minus 5.5 delta of n minus 4. That's all. That is the required answer. Okay. Now, let me give another problem for you to represent. So, let me say this is my y of n. Y of n is equal to minus 2, 1, minus 1, 0, 0, 4, 2, 3, 6. Okay. And this is the 0th index. All right. Convert this into the equation format using the delta representation. So first, let us plot this to understand how we can convert this into the equation. All right. Okay. So this is the x-axis. And I understand that this is the 0th index. On the right side, I need 0 means 1, 2, 3, 4. On the left also, I need minus 1, minus 2, minus 3, minus 4. So somewhere at the center, you will have the axis, the y-axis. Okay, so let me draw that. So let us assume that this is the y-axis. So this is the function y of n versus n. So that will be corresponding to the 0 itself. Okay, right. Now let me plot according to this. This is the index for minus 1, minus 2, minus 3, minus 4. Looks like it is sufficient. Now just draw the amplitudes as required. I have to go till 6 on the top. So this is 1, 2, 3, 4, 5, 6. And you have minus 1, minus 2. Okay, so on the left side, you can see that at minus 4, the signal amplitude is how much? It is minus 2. Okay, so I'll just write. So minus 2 is here. So this is the signal plot at this is minus 2. Okay, then minus 1, this is 0, this is 1, 2, 3, 4, 5, and 6. Okay, then you see the next amplitude is how much? Plus 1. So this is plus 1. And it is 1 at 3. Okay, then you can see the next amplitude is how much? It is minus 1. So at minus 2, draw the amplitude equal to minus 1. So this is the amplitude. Then at minus 1, it is 0. And at 0 also, it is 0. At plus 1, the amplitude is 4. Okay, and at 2 this is equal to 2, and at 3 it is a 3, and at 4 the magnitude is 6. All right, so this is the function. Right. Now you have to convert this into the equation, right? Just look at the position of the impulses or the delta functions and try to convert this into the uh, equation format. So the equation of this function y of n equals to -2 into delta of n plus 4. Absolutely perfect. Then amplitude is +1. So this is plus 1 into delta of n plus 3. Then amplitude is negative for the next sample, right? So that's why you write minus of 2, not 2, sorry, minus 1, I guess, right? Okay. So this is minus 1 into delta of n plus 2, right? Then two samples are 0. So you don't have to write them, directly go to the one which has a magnitude. So that is plus 4 into delta of n minus 1, and next one plus 2 times delta of n minus 2. Okay, then plus 3 times delta of n minus 3 plus 6 times delta of n minus 4 is the required answer. Okay, so this is how we convert any given signals values, discrete valued signal or function into an equation using the delta function. This is the first objective for us to learn the process of convolution. All right.